Buckling check on intermediate transverse web stiffeners. Stiffeners not subjected to external loads or moments should be checked for a stiffener force denoted by Fq, which is equal to V minus VCR by gamma m naught, which should be less than or equal to Fqd, where V is factored shear force adjacent to the stiffener, and VCR is shear buckling resistance, shear buckling resistance of the web panel designed using tension field action and gamma m naught is equal to 1.1, whereas stiffeners subject to external loads and moments should meet the conditions for the load carrying web stiffeners. In addition, they should satisfy the following interaction expression given as Fq minus Fx by Fqd plus Fx by Fxd plus Mq by Myq should be less than or equal to 1, and in this expression if Fq is less than Fx, then this Fq minus Fx will become negative, but it should be taken as 0, where here Fq is stiffener force given by the previous expression, stiffener force, which is given as V minus VCR by gamma m naught, whereas Fqd is design resistance of an intermediate web stiffener corresponding to buckling about an axis parallel to the web, and Fx is external load let us say external load this as Fx, then this will be our load bearing stiffener, and on the load bearing stiffener, if the load is acting at an eccentricity say E, this is the plan view, and this is end stiffener, and this is an intermediate stiffener, so Fx is the external load and Fxd is design resistance of a load carrying stiffener. This is design resistance of a web stiffener or intermediate stiffener, and whereas Mq is moment on the stiffener due to eccentric loading applied, so that is Fx into E. Our E is our eccentricity and Fx is our external load, and Mqd is yield moment capacity of the stiffener based on its elastic modulus about its centroidal axis parallel to the web, which is given as Tq into Lq square by 2 into Fi by gamma m naught. Buckling resistance of stiffeners, that is the buckling resistance Fqd should be based on the design compressive strength FCD of a strut using curve C. The buckling resistance FQD is given as effective area into FCD, where the effective section is the full area or core area of the stiffener together with an effective length of web on each side of the center line of the stiffener limited to 20 times the web thickness. That is, this area of the stiffener, that is our outstand BS, which should not be less than 20 TQ epsilon, sorry, it should not be more than 20 TQ epsilon, and for core section it is taken as 14 TQ epsilon, and this is thickness of our stiffener. Beyond that, the projection is taken as 20 times the thickness of the web from the center line of the stiffener on both sides. This is our effective area, and the design strength used should be minimum value obtained for buckling about the web or the stiffener. In this, FCD is given as Fy by gamma m naught by phi plus under root of phi square minus lambda square, where phi is given as 0.5 times of 1 plus alpha into lambda minus 0.2 plus lambda square, where alpha for class curve C, alpha is taken as 0.49 and lambda is non-dimensional slenderness ratio, which is given as under root of Fi by FCC, where FCC is equal to pi square E by KL by R whole square, where KL is the effective length, and the effective length for intermediate transfer stiffener used in calculation of the buckling resistance FQD shall be taken as 0.7 times the L, where L is length of the stiffener. Based on this KL by KL, we can find FCC, that is pi square E by KL by R whole square. Using that we can find FCD, and substituting we can find FQD, whereas the effective length for load carrying web stiffeners used in calculating the buckling resistance FXD, where FXD is design resistance of load bearing stiffener in which also the effective area is taken as area of the stiffener, say length of the stiffener as LQ and thickness of the stiffener as TQ, and for the core area or effective area calculation, web 20 times TW is taken on both sides, and in this case the effective length KL is equal to 0.7 times of L when flange is restrained against rotation in the plane of the stiffener by other structural elements, whereas KL equal to L when flange is not restrained, where L is length of the stiffener.